Good afternoon, and welcome to the Brain and Behavior Research Foundation Meet the Scientists monthly webinar series. I'm Dr. Jeff Borenstein, BBRF's President and CEO. Today, Dr. Ami Klin will present, quote, the crisis of access to early diagnosis of autism and emerging solutions, unquote. Early diagnosis of autism and emerging BBRF is the world's largest private funder of mental health research grants, supporting transformative discoveries in order to develop improved treatments, cures, and methods of prevention. The high quality of the research we fund is made possible by the BBRF Scientific Council. This group of 192 prominent mental health researchers reviews each grant application and selects the most promising ideas with the greatest potential to lead to breakthroughs. The Scientific Council guides the Foundation to fund creative and impactful basic, translational, and clinical research relevant to the whole spectrum of mental health. One reason that research funded by BBRF has had such great impact is because we do not limit our focus to one illness or condition. Since 1987, the Foundation has awarded $461 million to fund more than 6,500 research grants around the world and across a broad spectrum of brain conditions, including addiction, ADHD, anxiety, autism, bipolar disorder, borderline personality disorder, depression, eating disorders, OCD, post-traumatic stress, schizophrenia, as well as suicide prevention. Today, I'm delighted to introduce Dr. Ami Klin. Dr. Klin is the Georgia Research Alliance Eminent Scholar Professor and Chief of the Division of Autism and Developmental Disabilities at Emory University School of Medicine. He is also the Director of the Marcus Autism Center, Children's Healthcare of Atlanta. He was the 2018 Ruane Prize winner for Outstanding Achievement in Child and Adolescent Psychiatric Research. Our webinar will begin with his presentation, which will then be followed by Q&A. To submit your questions, please use the question tab on the control panel. Feel free to submit your questions at any time following the presentation. I'll ask as many questions as possible in the time allotted. And now I'm pleased to introduce Dr. Klin. Ami, the floor is yours.
Thank you so very much, Jeff. It is really an honor for me to present at this forum, Brain and Behavior Research Foundation, a foundation that has had a tremendous impact in our field. And welcome to all of you joining this webinar today. So I'm Ami Klin. I direct the Marcus Autism Center, Children's Healthcare of Atlanta, and Emory University. I would like to focus today on a crisis that those of us who are involved in the field of autism spectrum disorder have been experiencing for some time. What are the challenges and what are the opportunities in this field? The title of my webinar is Increasing Access to Early Diagnosis and Assessment of Autism by Objective and Cost-Effective Eye Tracking-Based Tools. But I could just as well title it as The Crisis of Limited Access, because this is our collective experience at the present. Before I start, I need to provide some general disclosures. Well, first of all, most of the work that I'm going to be presenting to you has been co-created with Warren Jones, a colleague with me for close to 20 years at Yale. Before I moved to Atlanta, we have worked together for many, many years, developing the science that eventually led to some of the innovations that I'd like to introduce today. Warren and I wanted for the science and technology to be disseminated to those who need it. For that purpose, a company called Early Tech Diagnostic was launched, and is in charge of disseminating this technology broadly. Most of the company is owned by Children's Healthcare of Atlanta, which is a large pediatric healthcare system here in Atlanta, Georgia, in the United States. And they have the commitment to turn any benefits from this company to treatment of autism. And needless to say, all of those activities are monitored by Emory University School of Medicine Dean's Office. So a little bit about my personal story. So my personal story is that I only had 2 adult jobs. The first one was at Yale School of Medicine for 20 years, where I used to direct the autism program there. We saw many children, and I had the privilege of working with luminaries in the field and help develop the gold standards for the assessment of young children with autism. These standards required the input of a multidisciplinary team conducting assessments that could last anything between 6 and 10 hours. It was wonderful, but the main issue is that it was not accessible to the community at large. Because of that, in 2011, I and many colleagues from Yale moved to the Marcus Autism Center here in Atlanta, and our major goal really was to ensure that we could leverage our science for the purpose of addressing the lack of access to those services. The Marcus Autism Center is the largest center of its kind in the country. It serves over 6,300 unique children every year, and now close to 50,000 clinical visits, about 530 staff. We have a large building, but we also have several locations. One of the major commitments that we have had as a center is to both lead and help co-create an ecosystem of care in our community. Very important for us to partner with all of the agencies serving family and of importance, all children and all families, and that includes the traditionally underserved populations of children from minority, low income, and rural families. So what are the needs that we collectively have? What are the challenges that we collectively face in this field? Autism is the most common complex neurodevelopmental disorder of all, affecting 1 in every 36 children. This sounds like an abstract number, but imagine that in the United States alone, over 100,000 children are born every year who will have autism. Now, many decades of science have shown that autism is not a disease. Autism is a genetic trait, and autism unfolds in the first years of life. And like any neurodevelopmental condition, the earlier we identify it and the earlier we intervene, provide treatments and supports to children and families, the better the outcome of children. In fact, we know nowadays that were we to be able to identify, diagnose, and treat children early on, we might be able to optimize their outcomes for their lifetimes. So what are the challenges? The challenges are that in this country, it is still the case that only 1 in 5 children with autism is diagnosed before the age of 3. In fact, the median age of identification is quite late, during school years, between 4.5 and 5.5 years. And by that time, we're no longer treating autism. We are treating, which is a social disability, we are treating the burdens of autism, which are the associations with intellectual disabilities, language disabilities, and severe behavior challenges. So, of course, we can provide treatments that are going to benefit children, adolescents, and adults at any stage of their lives. But early on, there is a window of neuroplasticity, age, basically the time in which young children learn the most. This is the window of opportunity that we have to truly have an impact on their lives. Families have been hearing this for quite some time, but access to expert clinicians who can provide the diagnosis, without which there is no access to treatment, is very limited. And the families are the victims. So no diagnosis, no access to treatment. And so this promise that early is better really rings hollow in the ears of many parents who are concerned about their children but cannot access services. Now, this phenomenon is now being called the diagnostic odyssey of autism spectrum disorder, something that is known widely, and it has become one of the national priorities to address. Well, just give you here an illustration from the state of Georgia, where I am. The American Academy of Pediatrics, since 2007, has recommended that all children coming to well-child baby visits at the ages of 18 and 24 months are screened for autism. And so there is a community uptake of the screening. Pediatricians are screening families, and once they are screened positive for autism, the Georgia Department of Public Health needs to find services. And right now, in every year, there's currently over 4,000 toddlers who have been screened positive for autism, but the Georgia Department of Public Health is able to provide access to diagnostic services to less than 10% of them. So there are literally thousands of parents who have been told that their children may have autism, but there is nothing that they can do about it, because if they cannot access diagnosis, they cannot access services. So this is the question that I pose to everybody that I talk to these days. Is this acceptable? Is this ethical? And is that equitable? The reason why I asked the question of equity is because whenever you have limitations in access, there is the great potential for the creation of healthcare disparities. And in our field, the healthcare disparities are stark. So this is just one example of a project that my colleague John Constantino and here in Atlanta, Dan Gashwin in Los Angeles, and myself have been running for quite a period of time. It's an autism center of excellence focused on the genetics of underrepresented populations, and in this case, focused on the African American community. Interestingly, this grant, even though it's focused on molecular genetics, has become the platform for us to study the healthcare disparities in our field. So in this study, for example, involving the largest cohort of African American children with autism, what we found is that the diagnosis, the access to diagnosis in this population is even later than the late access that other children have. And as you can see here, parents are on average waiting 2 to 3 to 3.5 years until they manage to access diagnostic services. What is then the inequity created? Well, here is the result. Black children with autism in the United States have almost double the risk of having lifetime intellectual disability than white children with autism. If we feel that this is unacceptable, then we need to do something about it. Now, in many different ways, diagnostics in autism has become an end, and it should really a means. It should be a means for treatment. Now, this problem does not happen in autism only. The national academies have reviewed diagnosis in medicine generally, and what they found out is that the problem of diagnostics in medicine is a huge challenge, but they believe that it can be improved. Not only that it can be improved, but that this enterprise represents a moral, a professional, and a public health imperative. So autism is not the only one, but the stark inequities in autism trouble us greatly. The other thing that we've learned is that, this great gold standards that we helped create in the past for the diagnosis of autism is, it's not gold. It's more like silverish. We completed a multi-site trial that I'm going to actually talk about later on today, in which we looked into these expert clinicians working in expert centers of excellence. How did they feel about their diagnosis of very young children with autism? And this is what we found. We found that those expert clinicians, in 30% of the cases that they diagnosed, they did so lacking confidence. So, as I said, not gold standard, maybe silverish here. Of course, the early diagnosis of autism is challenging in very young children when they're still developing and their symptoms are becoming more marked with age. It is still the case that it is like in a great portion of psychiatry, it's a subjective process. So because of that, there has been great interest in this country in developing a science that is going to reduce subjectivity and augment access to this service. And the way that people have been dealing with that is by trying to develop biomarkers for autism. A biomarker is an objective, quantitative measure that you can take in the same way and can be done in such a way that is going to reduce subjectivity and is going to increase productivity. So a biomarker needs to be objective, quantitative, it needs to be dimensional, it needs to be performance-based, meaning that it needs to come for the child, because it's often the case, particularly when you're working with under-resourced families, that the families don't have the wherewithal to provide us with the historical information needed. It needs to be standardized so that it's done in the same way for every child, and it needs to be able to capture the core features of the condition, and it needs to be mechanistically relevant, meaning it needs to help us advance research into the causes of the condition and innovations in treatment. So what we try to do is to enable high quality early diagnosis via objective, standardized, highly quantitative, and cost-effective technology that leverages the science that we have been involved with for the past 25 years. It's developmental social neuroscience, in other words, the science of early brain development. Now, the state of biomarkers in autism has been poor. This very influential recent review of the state of biomarker advancements in autism concluded, after reviewing many studies, that we currently do not have a biomarker with sufficient evidence to inform autism clinical trials. Very few things in medicine have advanced specific fields, like fields like oncology or Parkinson's disease or other medical conditions as much and as potently as biomarkers. The moment you have a biomarker, you can use it not only for diagnosis but to gauge a patient's change as a result of treatment. It can help us look into causative aspects of the condition. But in autism, we haven't done that very well. And one of the reasons is that there is a Bible for clinical trials in clinical medicine, and it's called the Standards for Reporting of Diagnostic Accuracy Studies. These are the standards that ensure that publications of clinical trials, they really meet the highest level requirements so that those results would be replicable and reproducible, and they would last. Well, my field, unfortunately, has not used this Bible until recently, and so the research in our field has been delayed by that, and these are important standards. There has been a lot of interest lately on using machine learning, deep learning, artificial intelligence to create such biomarkers. But the problem with that is that even though AI or machine learning can be a very, very powerful tool, because math is a very powerful tool, one of the big issues is that you have a lot of data and you have a lot of mathematical algorithms trying to find, let's say, patterns in those data, and you try to use it diagnostically, but there is a big problem with reproducibility of your results. So for those of you who read artificial intelligence studies in diagnostics, in medicine in general, and even in autism, if the study has not been replicated in an independent sample, well, it doesn't deserve a second reading. So this is just my word of caution for you there, okay? So what is our biomarker? What is that we have been trying to study for the past many years? We use this technology called eye tracking technology to measure what a child looks at and learns about in their surroundings. And we do so at the rate of 120 times per second. Okay, so looking and learning about the world around them. So here you see a video and you see a crosshair in front of you. And this crosshair here tells you exactly where a 2-year-old is looking at moment by moment when they're watching this video of two toddlers interacting. Okay, so this is what we do, and we measure this 120 times per second. Well, from the very beginning of our research, we really wanted to stand behind a child's eyes and see the world through their eyes. And because looking at and learning about the environment is a major platform for brain development, we needed to understand how children typically do that and whether there are deviations in the early development of children with autism. But there was a problem on how do you measure that? And this is how we try to solve this problem. But first, I'm going to show you a videotape. So this video gives you a sense of what is the battlefield of brain development when toddlers are basically exposed to other children. They are learning about the very basics of socialization, the basics of social understanding. They are looking at facial expressions. They are looking at the eyes of others because so much intention and so much of the emotion comes through the eye expressions. Also, what are these children paying attention to? It's going to give you what is going to give you a sense is what they are looking at, and even things that cannot be visible in the video, but they end up learning is what's inside these children's heads, which are the mental states, things such as intentions, emotions, and thoughts, and beliefs, and false beliefs. So those are the kinds of things that they will need in order to be able to navigate the demands of everyday social life. Those are the basic blocks of socialization. But how do we measure how children are processing this kind of information? So imagine that this is a frame of video and there are 36 frames per second. Okay? Now, what you're seeing here is a little equation. Now, what this equation is telling you is the amount of visual resources that one 2-year-old is dedicating to this spot of the screen at that moment in time. Now, this equation comes from basically the amount of photoreceptive cells that are capturing information right in the middle of what the child is looking at. This is something that we know from primates research of their visual system, and in photoreceptive cells, which are in your retina, they then lead this information to the brain, and there is something called cortical magnification, meaning that this little bit gets magnified downstream in the brain, which basically means that there is more brain tissue associated with processing information on this spot at that moment in time. So this is one typically developing 2-year-old looking at the screen at this spot at that moment in time. Now what you're seeing is 45 others that are also watching this video. And what you have here is basically a heat map. And the colors become brighter, like these reds, when there is convergence of children's looking behavior. So they are focused on the same spot of the screen at the same time. There is a convergence of visual resources. Now, let me give you a different perspective to look at. I'm going to give you now the bird's eye perspective. We call this a salience map. And what it tells you is that the bright colors like red here, there are more children are looking at that portion of the screen. A few are looking here, but none is looking in the blues, okay? Now that I have this representation, let's take let's watch the same video that you watched before, but through the eyes of 45 typically developing 2-year-olds. As you see, their looking behavior is changing all the time. But as a group, when something really important happens, for example, here in the middle of the screen, you get these really bright reds because they're all converging on that spot at that moment in time. We call that spot at that moment in time a hot spot of socialization. This is an entrainment. All the children are looking there because something really important is happening there that provides them with an opportunity for social learning, okay? Now, let's take another perspective. So this is one frame of video, and here you have the z-axis, which is the axis of time. And you're going to see that there are many frames of the video. We can now carve the salience map across time. And the result of this is a space-time distribution that we called an attentional funnel. This attentional funnel basically means that as a group, these 2-year-olds, as they're watching this video, here there is some dispersion, but at this moment in time, there is major convergence, one of those hot spots of socialization, because all the kids are paying attention to that spot on the screen at that moment in time. And so this is a space-time distribution, and that it is a statistically significant convergence, okay? Now we can watch the same video that I showed to you before through this attentional funnel, and you can see here on this panel these hot spots of socialization that are happening moment by moment because these young children are learning about the significance of this interaction. There are only bits that are really, really critical, but these are really critical bits because these are the opportunities for social learning, okay? Now, let me give you another example, and I'm going to stop right here. You see that all of these 2-year-olds are focusing on something that is happening between those two toddlers. The reason why they are focusing there is because unconsciously, they were able to process the information in the eyes of this toddler. This toddler is looking at the object. They are fighting over the object, and so the meaning of that social interaction is that they are fighting over the object. But they are able to get this gaze cue that gives them a direction of this toddler's attention focused on something in the middle, and they're all now paying attention to that in the middle. If they don't look here, they won't know what the social interaction is about, okay? So this is a data-driven empirical way of basically allowing the children to tell us moment by moment, 120 times per second, what is of importance that they are looking at, okay? So just to give you an example, this is one attentional funnel for the typically developing 2-year-olds crossing this frame of video. And here, what you see are scan paths of 2-year-olds with autism watching the same video. This is what the typically developing children are looking at and learning about facial expressions and communication. And this is what the 2-year-olds with autism are learning about, that door opening and closing. These children are becoming experts on people. These children are becoming experts on physical things. Now, that was only one illustration. What we found out is if we have these children watch 10 to 12 minutes of video, that in fact there are many, many, many divergences in the children with autism relative to the typically developing children. In fact, there are thousands that happen within the context of 10 to 12 minutes of video. And that's the level of quantification that we were able to leverage in order to create a diagnostic device. But what does that mean? It means that, that thousands of times the children with autism are missing those opportunities for social learning. Of course, this is not happening only in our experiment, it's happening in our daily lives. And so every time that they're exposed to social stimuli, what does that mean? It means that this is the model for autism. Autism is a genetic trait that predisposes these children to miss those opportunities for social learning at the rates of thousands of times over the first 2 years of life. And here are additional examples. So this boy here is pointing to something, right? This is a picture taken from one of the videos. This is where the typically developing toddlers are looking at, and this is where a toddler with autism is looking at. This is another scene taken from a video. This is where the typically developing children are looking at, and this is where a child with autism is looking at. Multiply this by hundreds and hundreds and hundreds of times over the course of a 10 to 12 minute previewing of social interaction in those videotapes. So you saw the biomarker, but remember that we needed to validate the clinical significance of that biomarker. So we tried to do that over the past 20 years. And but before that, I need to provide you with some foundational concepts. Even though autism is one of the most strongly genetic and heritable of all brain conditions, the genetics of autism is extremely complicated, and nobody has been able to go from genes to behavior or to the condition itself. And the reason is that for the vast majority of children with autism, this is a condition that is the quintessential polygenetic condition. There are many, 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 many hundreds of genes associated with this liability, each one of them conferring just a bit of risk for the condition. And so we cannot go directly from genes to autism. And our working hypothesis is that this genetic trait, what it does is that from very early on in development, it disrupts the path of socialization. Every child needs to learn to interact with others. They need to learn to speak, to acquire language, to be able to communicate with others, to interact reciprocally with others. And that's the platform of brain development that is disrupted by the genetic liability in autism. And if so, we can actually make a clinical diagnosis of autism only in the second and third year of life, when the symptoms have become so prominent that we cannot miss it anymore. But the process has begun really from the first hours and days of life, as children's socialization became disrupted, and the results thereof became the symptoms of autism. So in order for you to fully understand that, I need to start from the beginning. And so human babies, they are born in this utter state of fragility. In fact, if they don't have any caregiving, they would die. So fragile they are. So nature has endowed human babies with this, let's say, this biases towards people, because without the other, they will not survive. So from the first hours and weeks of life, anything that sounds like caregivers, smells, moves, looks, interacts like caregivers, is going to command the baby's preferential attention. So babies are born to socially orient because their very survival depends on it. And then babies are oriented to their caregivers. Caregivers are also biologically oriented to their babies, and it is this mutually reinforcing choreography, something that we call reciprocal social interaction, that moves early brain development forward. It's that engagement, is that interaction. So keep that in mind. A third concept that is very important for you to keep in mind is that babies' brains are more like spaghetti when they are born. By the time that babies that we're celebrating the baby's first birthday, the baby's brain has doubled, and synaptic density, which is an index of the amount of reorganization of the brain, the connectivity among different brain structures, and that also reflects this baby's early experiences, has quadrupled. So the year with the greatest neuroplasticity or capacity for learning in human beings is in the first year of life. Now, we can always learn, of course, even as adults, even at my age, but the fact is that that tremendous window of learning that the brain affords us in the first years of life is a window that eventually is going to close, and it's going to become more and more difficult to change things. So keep that in mind. This concept is important because even though there is genetics that is moving brain forward, as genes become proteins and proteins build brains, we as a species, we are born extraordinarily plastic, so that the experiences that we have, the early experiences that we have, become instantiated as well as brain structure and connectivity. So early experiences matter a great deal, so keep that in mind. So now that you have that, our biomarker, we call it social visual engagement, the way that children look at and learn about the world. Because autism is such a heritable condition, we needed to find out whether this behavior is influenced by genetic variation, meaning what is the genetic structure. So my colleagues, John Constantino, Warren Jones, and I engaged in this research with twins. They're identical twins and fraternal twins. Identical twins, they basically share 100% of their DNA. So they're carbon copies of each other. Fraternal twins, they share 50% of their DNA. So if you want to find out if a particular behavior is under genetic control, you basically study identical twins and see how much agreement exists between the two twins, and then you study fraternal twins, how much agreement, and then you compare the agreement between identical and fraternal. If there is a huge difference between the two, then we know that this behavior is under genetic control, and that's exactly what we found out. This is a complex slide. I just want you to pay attention to what I'm putting my cursor on. Among fraternal twins, dizygous twins, when we put those two fraternal twins in two separate rooms and have them watch our videos, they basically agreed, or they watched the video similarly 35% of the time. For the identical twins, the agreement was 91%. So remember, those twins are watching those videos in separate rooms, but 91% of the time, they will be looking at the videos at exactly the same way. And so what we realize is that in typical development, these children are not only reacting to those videos, they are seeking specific information out there in the environment. Actually, we found out that there was agreement among the identical twins at microscales of tens of milliseconds. What does that mean? It means that not only that they are reacting to something they are seeing, because there is no time, tens of milliseconds is only a couple of synapses away from the retina, but they're actually seeking the information out there, and they are genetically predisposed to do so. In other ways, they are creating their own world. The bottom line is that we as a species we are born to interact with others. Okay. Here, just to illustrate, these are fraternal twins watching our video, and you see the two crosshairs right in the middle. And what you see is that even they watch these videos in separate rooms, but we brought it together for you. Is that there is some agreement, but not a tremendous amount. What about identical twins? Remember, they watch those videos in separate rooms. So you see, this is the level of agreement. They are basically watching this video very much the same. Okay. So interestingly, now that we knew that that social visual engagement, our behavioral biomarker, was under strict genetic control, meaning highly heritable, we then tested 2-year-olds with autism relative to those typically developing twins. And what we found out is that these markers could actually segregate the children with autism. So the gray balls are typically developing children, and the red balls are 2-year-olds with autism. So you see, the same marker that is highly heritable is segregating 2-year-olds with autism in the first study and then in a replication study. So what we realize is that this behavior, which is genetically based, is disrupted in autism. So they are not creating a social world inside their heads as they're typically developing peers. And that happens moment by moment by moment. Okay. Now, what is the other sort of line of studies that we did? Autism really emerges from very early in life. So we needed to figure out if this behavior was something that differentiated babies who eventually would receive a diagnosis of autism. And in order for us to do that, we studied high-risk babies, meaning babies who are at elevated risk for autism because they are the younger sibling of a child with autism. If I have a child with autism and I'm having now another child, 1 in 5 of the young children will also have autism. That's the reason why it's considered to be so highly heritable. And we followed those babies from the age of 2 months monthly, and then periodically until the age of 24 months when we could make a diagnosis. The red line is for babies who eventually were diagnosed with autism. And here are low-risk babies who eventually had a typical development path, okay? Now, this is percent of fixation time on the eyes. The eyes are not only the window to the soul, the eyes are also the window to the social brain. And what we found out is that the typically developing children would increase eye fixation in the first months, decrease for a period of time, and increase again. And the reason why they would decrease during 9 and 15 months is because they would focus on the caregiver's mouths, because they realized that the mouths of the caregivers were transmitting information about speech, and they are learning to make their very first words. And when young children learn the first words, they use the movements of the mouth of the caregiver to segment sounds into words. But this is needed only for a period of time. Later on, when they can already speak, they go back to looking at the eyes because they need now to decode the intention of the speaker or the emotion that the speaker, or even the referent. What is that word related to in their environments? With the children with autism, here they start all the way up here when they are born, but then it's free fall for the first 24 months of life, which basically means you are seeing autism unfolding right in front of you. And what we found out is that data from the first 6 months of life was highly predictive of the diagnosis of autism and level of disability at the age of 24 and 36 months. So that's another line of research validating this biomarker. And finally, very quickly, we are not the only species that needs caregiving. All primates need caregiving. And so we also studied this behavior in infant monkeys. The only thing is that infant monkeys, they mature 4 times as fast as human infants. And so you need to make a transformation on the data. Here is the percent fixation at the time in typically developing human infants. And here is percent of fixation on the eyes in infant monkeys. And you see that the curves are literally identical, literally identical. And what does that tell us? It basically tells us that nothing really is more important in shaping the primate brain than the fact that we are born really fragile, we need caregiving, and we need to live together. Otherwise, we shall not survive. But this is very important for us because we could see that this biomarker that we develop is highly conserved phylogenetically across species. So I told you a great deal about, hopefully, this biomarker and its science. How could we leverage this in order to create a solution for greater access to high quality early diagnostic services? So what you see here is what our typical eye tracking laboratory looks like with the size of a room. And so when we moved to Atlanta, we basically built a new building in which we would start miniaturizing this lab into something that will be a little more portable, something that could be used, for example, in multi-site clinical trials across the nation. And this was the prototype that we were able to create. And immediately, because we wanted this solution to be used clinically very broadly, we contacted the Food and Drug Administration of the United States in order to basically start working with us. Our goal was to show that this would have clinical validity and that we would be able to use this broadly in the population. And for that, you need FDA approval. So we began our communications with them. They began to inspect and audit our labs. We changed all of the computational aspects of this tool from something that was more artisanal, more like research-like, created industry standards, and also had to do a whole bunch of repeatability and reproducibility studies, which is basically a baby needs to be seen in 2 different devices. We need to show that there is comparability, that kind of a thing. And more recently, we are able to transform this device, which still had the size of half a refrigerator, into something that is now basically an iPad-like device right here in front of you, okay? But we also needed to validate this clinically. And so we wanted to match the 12 minutes of our procedure against the gold standard evaluation, the 6, typically 4 to 6 to 8 to 10 hours of evaluations conducted by expert clinicians, of course, using the best standards for diagnostic studies in medicine. The notion that we could come up with a device that would do in 12 minutes what expert clinicians take 6 to 10 hours is a kind of an extraordinary claim. And so we needed to make sure that we would not make that claim until we had extraordinary evidence. And our various different clinical trials were published in September of 2023. They were published simultaneously at the Journal of the American Medical Association and one affiliated journal, JAMA Network Open. But the publication was coordinated by the editors of JAMA. And what did we try to do in these clinical trials? We leveraged this quantification that we developed that I showed you in order to model the diagnostic classification given by expert clinicians completing that lengthy diagnostic assessment. But we needed we wanted to do more than just be able to provide a diagnosis, because there is a spectrum of autism, and if we want to personalize treatment to our children, we also need to know how socially disabled the child is, and we model the reference standard in this domain, the Autism Diagnostic Observation Schedule, but also how much language the child has and how much nonverbal learning capacity the child has. And we model a reference standard test for that called the Mullen-Early Scales of Learning. All right. And this is basically the two large studies that we conducted. The first was a discovery meaning that we're developing our algorithms and then we replicate it. And then there was a pivotal trial. Both of those studies were multi-site. There are over 1,600 toddlers, 7 specialized centers around the US, 1 community real-world health center, 2 real-world replications, 3 independent cohorts, and 1 repeatability and reproducibility study. This is just to give you a sense of this population for the first study conducted with Washington University and us. This is the different sites for the pivotal study. The 6 sites were in Phoenix, in Atlanta, Seattle Children's, Cincinnati Children's, University of California, San Francisco, and Rush in Chicago. Just a word about the samples that participated in our pivotal study. So you see here 185 toddlers aged 16 to 30 months, okay, without autism, and 150 with autism in this case. The important thing for you to know is that these were not 185 children without any diagnosis. Over 87% of these children had other conditions, other developmental conditions. And the reason we did that is because we wanted to make sure that in clinical trials, we will have a diagnostic composition of samples that will be typical of centers, of diagnostic centers serving children with autism and other neurodevelopmental disabilities, okay? And these are the results. So forget about the discovery study, but here's the replication study, and here's the multi-site pivotal trial. And here are the results that you see. You see that it's, this is a replication, and this is the second replication in this multi-site trial. This is the percentage of children who the clinician said yes for autism, and the device said yes for autism. The percentage of cases that the clinician said no for autism, and the device said no to autism. This is the probability that when the device said yes for autism, the child truly had autism, or no to autism, the child really had no. So these are numbers that are coming very close to the performance of something like a strep test in a pediatrician's office. Now, could we measure a child's level of social disability? Could we proxy the autism diagnostic observation schedule? In fact, we could capture over 73% of the variance in scores. Basically, we were able to generate a proxy for that procedure that takes about an hour and requires an expert clinician trained in that particular test. We could also proxy a measure of verbal skills. 75% of the variance of verbal skills we could actually capture. So in a way, another test that may take up to an hour, but we could do that very quickly. And here is nonverbal skills. We could also capture up to 74%. In other words, this 12-minute procedure was shown to provide an objective measure that can effectively proxy expert clinician diagnosis and comprehensive evaluation of symptom severity in children aged 16 to 30 months, but to do so in a short period of time, objectively and quantitatively. So this test then received clearance by the FDA, and the first few children were seen clinically in August of 2023. So that's the idea. Relative to 6 to 10 hours of expert clinician evaluations, this test is a 12-minute procedure. A clinical report is produced about 15 minutes later in an automated fashion in a secure server, and the clinician then can download that clinical report. It provides not only a diagnosis of autism versus not autism, but also the positive predictive value, negative predictive value, as well as these quantitative indices of severity, both for social disability and verbal and nonverbal learning. Okay, so what does it look like these days? So now I'm going to show you a video, and hopefully it's going to work.
For children with autism, the earlier the diagnosis, the better the long-term outcome. Unfortunately, fewer than 20% of children with autism are currently identified before the age of 3. That delay in diagnosis leads directly to delayed intervention and delayed treatment. However, with the EarliPoint evaluation, we can test children between the ages of 16 and 30 months, assessing their progress on the core dimensions of autism over time. Typically, developing children viewing videos tend to focus on the same area of a scene at the same moment about 80% of the time. The looking behavior of children with ASD tends to differ, such as focusing on objects rather than faces, with important learning opportunities being missed in every social interaction. Using interpretable AI, EarliPoint assesses individual looking behavior at a rate that is imperceptible to the human eye, measuring hundreds of focal preferences per second and then comparing those data to significant attentional moments for typically developing peers. This attentional funnel provides the clinically validated reference standard that gives parents, caregivers, and providers timely, objective, and accurate information concerning potential developmental vulnerabilities, allowing for earlier identification and treatment for ASD.
So I'll be very quick in just summarizing things. What are next steps? The FDA cleared this tool as a diagnostic tool for the early diagnosis of autism, but the problem is that in our ecosystem of care, our current screeners, the very screeners that are used by pediatricians, are not working very well. In fact, the most widespread screener nowadays misses more children than it actually identifies. So we have several studies going on right now in which we test this technology as a population-based screener to be used by pediatricians in well-child visits. We're also, we focus on young children because of our opportunity to identify children earlier and optimize their outcomes. But it turns out that most children are still being diagnosed later. So we are just completing clinical trials now that are extending the FDA indication from 16 to 30 months all the way to 7 years, where we also completed clinical trials testing this biomarker as a way of measuring change in children as a result of their response to treatments. Those two things we have already completed. We are able to provide positive predictive value and negative predictive value, which are quantitative information about confidence that clinicians should have in the results that we provide them. We also provide now those reports that can be incorporated into the clinician's own reports so that they can save time. And moving forward, we are developing indices for behaviors that are target in specific treatments so that the provider of treatment can actually be informed by how the child is doing in that particular skill, week by week. And we are supporting research networks that are now moving on to have more objective phenotyping of the cases that go into, say, research in genetics and neuroscience and so forth. Why have we been doing that? Because autism is not a disease. Autism is a trait. We're not here to cure autism. We are here to ensure that we optimize these children's outcomes so that they can live productive lives. And in order for us to do that, our very best opportunity comes from identifying children early and then providing the treatments and supports that they need in order to succeed in life. In other words, we want to change the narrative of this condition from one of disability to one of possibility and promise. A few references, thanks to all of the foundations that have supported us over the years, the many people who contributed to our multi-site clinical trials, and the many faculty and students who have worked with us for many, many years. So I'll stop sharing. And Jeff?
Yes. Ami, what an extraordinary presentation on such impactful work that really can make a difference in so many lives. So I want to thank you for the work that you've done, for sharing this with us, for the work that you're going to continue to do. We don't really have time for questions, but your presentation was just so outstanding. I think you answered many of the questions that we received just in the scope of your presentation. So, I want to thank you for that.
Well, thank you so very much. Thanks to the Brain and Behavior Research Foundation for the work that you do to advance the science in this field. And thank you to everybody who tuned in today to hopefully learn some helpful information, and particularly for those of you who are impacted or provide services or support families who are impacted by autism. Thank you so very much, Jeff. Thank you, Nico, for all of your supports. Bye-bye.
Thank you. And I want to remind people that this webinar has been recorded. If you've missed any portion of the presentation or would like to share it, please visit the events and webinar page on our website. Please join us again on March 11th at 2 p.m. Eastern Time when Dr. Anya Bershad, Assistant Professor in the Department of Psychiatry and Semel Institute for Neuroscience and Human Behavior at UCLA, will present emerging treatments for social disconnection in psychiatric illness. Once again, thank you. Remember, together we can dramatically improve the lives of those living with mental illness and enable more people to live full, happy, and productive lives. Take care. Thank you.